Okay, in this video we are going to solve this problem here, this 24. Okay, so there are two problems on this slide. The 24 is with respect to this figure here. The 25 is going to be solved in the next slide, in the next video, and this is with respect to this figure here. Okay, so let's read this problem above. What we have is a proton. So it's a single charge now. It's not current, but a single charge. And it has a certain speed. It's given to us. I'm going to write this here. This speed is 10 to 6 meters per second. Very high speed. And it is in a magnetic field. Well, we don't know yet what is the magnitude of this field. We don't know the direction of this field. We know that this proton feels a force. I'm going to write here the magnitude of this force of 10 to minus 14 newtons. It feels a force. Now comes information about the direction, okay? It feels this force to the west, and now look at this drawing. West means to the left, okay? And you see here. And so east is to the right. So it feels a force to the west when it moves vertically up. Okay, so up is in this direction and down there. Well, we need a third direction to define the magnetic field. Okay, and the third direction of this story is going to be into the page or out of the page. Okay, and in this problem, they will say that into the page is north and out of the page is south. Okay, so what are the directions that we have here? Up and down, west and east, and then into the page is north, out of the page is south. Okay, so let me read again the story about the direction. So the charge, the proton, positive charge, feels a force to the west, so it feels a force to the west when this charge is moving up. Let me use the colors that we were using before. So the force is to the west when the velocity of this positive charge is pointing up. Okay. The problem tells us more. It also says that when this charge is moving horizontally in a northerly direction, remember what is north? Into the page. So when the velocity of this particle is into the page, this scenario here, then there is no force. Then in this case here, the force is 0. So why do you think they give us these two pieces of information? You see, when we have that the charge is pointing up, so if I'm going to use this positive charge, we use our hand, our 4 fingers pointing up. They say that the force is to the west, is to the left, so that means my thumb is to the west, is to the left, which means that my palm is into the page. Okay, so that could make us believe that the direction of the magnetic field is into the page. But remember, when we wrote the equation for the force, when I have a charge, is Q, V, B, and there is a sign of theta in this story. So I do not know if V, the velocity, and B, the magnetic field, are exactly perpendicular. They could be, but to be sure about that, that's why the problem gives us this, gives us more information. Also tells us that if the charge goes exactly into the page, then there is no force. Then this part here, this is what is really telling us, okay, so the magnetic field is really into the page, because when the field and the velocity are exactly in the same direction, that's when the force becomes 0. Okay, so this piece of information, what it's telling us is that the magnetic field, well, at least a portion of it is going to the page, but it could have an angle. Now it could be going partially into the page, so it could have an angle theta with the velocity. So it doesn't mean if I only tell you about this, you don't know yet if the direction of the field is exactly perpendicular to the velocity. It's only when we tell you about this piece of information that tells us that the magnetic field is really into the page. All right, so I repeat, what they are telling us on this right side. If the particle is moving into the page, then there is no force, which then means if the particle is going into the page, it has exactly the same direction of the field. That's why there is no force. Okay, so this part here, this part B, no? So from part B, we conclude that magnetic field, the direction of the magnetic field is into the page. Okay, because that prevents any force once I throw the particle into the page. Okay, now that I know that the magnetic field is into the page, then I can come back to part A. In part A, what do we then have? We have the particle, now the charge, the proton moving up. We already know from part B that the magnetic field is into the page, and the force is to the left. So in this part A, well, we know that in this part A, velocity and field are exactly perpendicular, so we know that theta in this case is 90 degrees. Okay, so after all that, now I can compute the magnitude of the force. How do I do that? Oh, sorry, the magnitude of the magnetic field, right? So we use this equation. The force is equal to Q, V, B, and now sine of theta we don't need to put because sine of 90 degrees is 1. So I can use this one now to get the magnitude. So we put here the value of the force, 8 10 to minus 14. Q, what do we have to put? Is the charge of the proton. So is that old 1.6 10 to minus 19 that we had talked before. And then V is that 5 10 to 6. And then from here we are going to get the magnetic field. And you see here the magnetic field, 0.1 Tesla. Okay, so again I repeat, only this part of the problem, only A, does not tell us for sure what is the direction of the magnetic field. It suggests that the magnetic field is somewhere going into the page, but we don't know yet if this field is exactly perpendicular to the velocity. It's only when we read about part B then we find out, okay, so this magnetic field is into the page, because if the velocity is into the page, then there is no force. The fact that there is no force, I know then that the magnetic field is into the page. After that, we can go back to part A to get the magnitude of this magnetic field. Okay, so this is the end of this problem.